So now that Mina is here, we can start. So it's a great pleasure to introduce Andras again.
You need to introduce me again. It's the same Andras as yesterday.
Yeah.
So yeah. So can I continue?
Yep.
So it's a continuation of my yesterday's talk. It's going to be, but I'll make it a little bit less elementary maybe than yesterday. So so this is the purpose of this work is to prove this formula that we saw yesterday. So I explained it a little bit. So let's just go very quickly go through it again. So it's absolutely remarkable that you have two. Essentially, we have our space M0 of rank R, semi-stable, moduli space of rank R semi-stable bundles. And of degree 0, and then the rank are stable bundles of degree 1 on the Riemann surface of genus G, that G that appears here. And then what we do is we put almost the simplest imaginable generating series. So we the only little modification, we multiply this R by PR minus 1. And so then we take the Poincare polynomial with the usual change of sign that appears everywhere. So that just means the odd cohomology has negative sign, and then the even has positive sign. And actually, we don't need it. It's just ordinary Poincare polynomial of those spaces. We make a shift. The shift is very, very important. In particular, the sign is important. We make a shift 1 minus g to the power r squared, and then which is roughly half the dimension, and then we construct a generating series where Q just records the rank. So we put all these spaces together, and then we just construct an identical thing, except for this one. It's not there, of course, because it's an identical for the 0. And then if you take the plathistic exponential of this, then one is transformed into the other. That's the formula. And so I explained a little yesterday, this plathistic exponential is essentially the invariant part, it's the Poincare polynomial of the invariant part of the nth tensor product of homology. So this plathistic exponential is actually simply a operation on polynomials. You take a polynomial which you think of as the Poincare polynomial of the variety. You put the usual change of t to minus t, and then what this transforms into is that basically what you do. So let's just maybe do a quick example. Say if I look just at x to be, say, the circle S1, then this formula is going to be just so you have the negative, the odd cohomology will be in the numerator, and the even cohomology will be the denominator. So you get something like this: 1 minus t times q divided by 1 minus t, 1 minus q. Something like this. So this is the odd cohomology appears at the top, the even cohomology at the bottom. And that's and then you look at this generating series in Q and you develop it, and then that's it. Right? So
may I ask you, is this kind of a refinement of McDonald?
So this is the McDonald formula. This is not. It's called McDonald form. Just explaining what it is. What is a little bit subtle here, I mean, not subtle, but when one has to pay attention, is this thing here, this shift. So usually, of course, you multiply something by a power of t, and it doesn't change very much a polynomial, right? A polynomial you multiply by t, nothing happens, and it's not such a big difference. But this sign is very important, because remember here, it was important what was odd and what was even. So this sign changes that notion. And so the even cohomology becomes, if the sign is there, and that means it depends both on genus and on the rank. So if the rank is odd and the genus is even, then there is this sign appears, and this sign means that everything that was odd becomes even, everything that even that becomes odd, and that changes what you retain here. So this actually plays a role, and that's actually how first that we found this. I'll explain it at the very end. This is crucial. Okay, so as I promised, so let me start by explaining the geometry behind. The whole point of this work is that that this is has a very concrete geometry behind it. This form and this geometry I'll explain. This is easy to understand. Now later will be some maybe more sophisticated things, but the geometry is very simple. And in fact, I'm very happy because this geometry is in what my thesis was based. It's so-called Hecke correspondence. It's a little difficult to explain why it's Hecke correspondence, but it's related to the Hecke operators in modular forms, but it's a geometric version. So let's see. So that's the Hecke correspondence. Okay, so now I'm explaining the geometry behind the formula. So the idea is the following. Remember, we have this with Riemann surface. We fix a point. So this will be, or this point is fixed from forever. And we do the following. So remember, we have stable bundles. So what you need to remember is just this degree 1 bundles and this degree 0 bundles. Okay, so one has degree 0, one has degree 1, holomorphic bundles. This P1 is a very simple thing. So it's essentially you just take a degree 1 bundle and you take the fiber of that bundle. So let me do a little picture here. So this is this point P, and over the point P you have this bundle, the fiber of the bundle. This is VP. This is a vector space of rank R, which lies above the point P. And what we do is that we fix a well, we don't fix, but the data is a codimension 1 subspace. So the rank of H is R minus 1. It's just a vector space in the fiber. So remember, VP is just a rank R vector space, and then H is a rank R minus 1 subspace. That's all. That's the data. It's very simple. Okay. I mean, as I said, I'll explain. I mean, this P1 is a very simple space. Basically, it's you take this moduli space, which is a smooth projective variety, and then you simply, this is just a PR minus 1 bundle over it, because for each concrete bundle D, obviously the choices of H is just the projective space. It's just what is a little less obvious is what this map is. Okay, so there's actually, so there's a slightly more sophisticated way of looking at it, but let's just I have maybe I'll explain it in a simpler scale, maybe not the most sophisticated way, but here is what is this Hecke correspondence? It's the following construction. So this is actually a statement here. So what I mean is that I have P1 and it's the same P1, and this picture describes the correspondence. So remember, correspondence essentially is a what is a correspondence, right? It's a correspondence. It's just a subset of the product. So this P1 can be thought of as a subset of the product of these two varieties. So I'll explain when two of them correspond to each other, when two are related. So I take a V here in M1, and I take a W here in M0. So when are they related? So the idea is the following: they're related if there is a bundle map from, so these are holomorphic bundles, so there's a holomorphic map from W to V. So there's another space, so there's other bundle here. So here there'll be another bundle W of the same rank as V, where it maps W to V, and it's always of full ranks. It's always of rank R over every point, except for this point P. And at this point P, the image of W is precisely this H. So the idea is that the kernel of this map eta for every element Q, for every point Q of the surface sigma is always 0, so it's always an isomorphism of vector spaces, except for the point P. There it's codimension 1. Okay, so that's the correspondence. So there's another way of saying this, but that's the idea. And so this way and the statement is that this way you obtain a dominant map. And so here the fibers are, so let me just write it here, the fibers of this map. So here the fibers are just PR minus 1. So this is all kind of obvious because for the vector space VP, I choose the hyperplane, that's PR minus 1. And here, of course, generically, minus 1, generically, but then not always. Otherwise, it's kind of complicated. So the generic fiber is PR minus 1. This can be easily seen, so I don't want to go more into this thing because I explain the rest of it. But generically, it's also PR minus 1. But then there are some places where it's different. It would be very complicated. Okay, so I'll discuss actually what the fibers roughly look like. But here I hope it's clear that this is PR minus 1 on this side. Okay, so in particular, I mean, so one more little remark here that, okay, if you accept this, that this is a smooth variety with a PR minus 1 bundle, then it's the usual Larey-Hirsch argument is that the cohomology, the Betti numbers in any case, it's not really a product, but the cohomology looks as a module, as an H and one module at least, it looks like the product of it of PR minus 1. PR minus 1. So it's just the product of it. Okay. Okay. So that's the situation, and so now I'll explain a little bit. This is the geometry behind this formula. Okay, so now I explain how the two come together. Okay, so let me just a minuscule, absolutely introduction to intersection homology, and that's the following. So the idea, so I gave the axiomatics, the intersection homology last time, so that's just roughly a generalization of what I call the cohomology package, but for singular varieties. So now I'll tell you here on this is just how to calculate it, so what it is actually. Okay? So if you actually read the books, then nobody's going to tell you this immediately. People will tell you also different things, but actually, in reality, for us, this is what this construction is the important one. So what's the following? So as I did for, so we assume that M, the variety M, is a stratified space, and these MIs are the strata. And now, so now the point is the following. The way we'll look at it, this was I think the Link's point of view. So if you just want the usual cohomology of M, then this is just the cohomology or hypercohomology of this Q is C, Q, what is QC, sorry. Okay, so what I mean is just you take the QM just means the constant sheet, constant over M. If you take the cohomology of the constant sheet, then you get the cohomology of the variety. That's so the definition that you use check cohomology and get. So the point is that intersection cohomology you can also obtained as the cohomology of a certain sheaf, but a different one. And this sheaf is called the intersection cohomology sheaf, and I changed next to M and here I don't. Okay, so it's another sheaf, and I'll explain what this sheaf is, what the intersection cohomology geometrically what it means. It's true, it certainly is true if the variety is a projective algebraic variety, which is what we have here. And so, roughly, well, it's sort of you have to study this fiber by fiber, but what you do, you take a point in one of these strata, this MI is one of the points, and then you just look, and PM is just the neighborhood of the strata. Okay, so you take just a disk around it, look at the neighborhood around the stratum, And then the point is that it's going to be a cone over a projective, also singular, possibly variety, which I denote by yi. Okay, so the idea is that the singularity looks like this. So you have stratum, but then there are higher dimension strata, and then somehow, and then what you do, you take a little neighborhood, and then the neighborhood looks like, that's what's important, is that it looks like, when I blow this up, it looks like a cone over something that itself might have some singularities, and this something is this yi, because it's a cone over something. Okay, so I take this yi, and now this yi, by induction, suppose I already know for a smaller dimensional thing what it is to look at intersection cohomology. This is intersection of this yi. And then I need to take the primitive cohomology of that of the intersection cohomology of y. And the primitive cohomology is the usual, Lefschetz primitive cohomology. It's the part that's not in the image of that omega operator that I was talking about last time. So I mean, if you don't know this, I don't want to define this now, but it is some part of the intersection cohomology that comes from the Lefschetz operator. Okay. So that's so the point is that so if you take P, so a point in this MI, so the algorithm, so I'm describing an algorithm. So you take this point, you look at a neighborhood, you represent the neighborhood as a cone over a projective variety. Over this variety, you calculate its intersection cohomology by, because it's lower dimensional, supposedly you know how to do it. Then you take its primitive cohomology, and this primitive cohomology will be what's called the intermediate extension of M to this stratum MI. Okay, so you find what I mean is this ICP. You'll find I described what the fiber of the sheaf is over that point. So it's a bit complicated, but at least it's concrete. I actually told you what it is. And it's still only, of course, I told you what the fiber of the sheaf is. It's a locally constant, thing. Obviously, it doesn't change, and this will be constant along stratum. So in a stratum, it's a constructible sheaf. It's locally constant. And then, like this one, but it's a bit more complex. And then now you take its cohomology of this sheaf, and that gives you what the intersection cohomology is. So roughly, this is an inductive procedure. It involves, but at least it's what I said is completely concrete. When you go sufficiently down, this yi will become smooth, and that will be our case. And then it's just usually cohomology, and it's just you take the primitive cohomology, usual cohomology. And again, primitive just means that you take you consider the multiplication by the Taylor class, and then you take the primitive elements of that representation of SE2 or SL2 that you have using the Lefschetz theorem. So I won't use all this, but I just wanted to show you how we in our work look at this. Okay, so it's a concrete algorithm, and we actually do this. So of course, this looks pretty scary, and that's probably why people didn't try it, because it looks kind of scary, but we actually did it. So we just calculate all this, and then it comes out. Okay.
So you're using the usual complex topology for these neighborhoods?
Yeah, so what we use, I shouldn't explain that in there, so I can tell you. So what we use is this usual deformation thing that you, for bundles, it's very simple. It's H1 of NV, right? That's roughly the deformation constant, and then you divide by the automorph. So what you will use, actually, it's a good question, maybe I'll answer it here. So this NPM, so let's V be one of these, and it doesn't matter in any open moduli space, it doesn't matter which one. So you just use this, and then, so this is a point. So now you think of a vector bundle, which is an element of the moduli space. Okay? And so then what I'm saying is that the local model is, well, if it's smooth, then it's just, so this NV, so instead of the point P, I put V now, is equal to roughly the following. You look at H1 of NV, and then you divide by out, something like this. And so of course, if there's no automorphism or just a trivial ones, then you just get. So this is rather it's actually maybe it's already this y. So this is rather. You can already think of that this y. So this is compact. So you just so this is our calculation. We use this h1n, and then you need to divide by the, and this is this quiver that we're discussing. Okay, so divide by the modulus. So if v is stable, then this out v, as usual, as it's well known, is just c star, and then you just get kind of projective space, and then n v is just the vector space. The vector space is the cone of a projective space, right? And if it's more complicated, then you get some toric quotient because well, if it's toric, and you will get to that. Okay, toric, but you could also in principle get a non-toric quotient if the isomorphism is more complicated. But that's the model we use for this tool. Okay, so so now so this is one data, and so then if once we get this, then of course these L's are so these local system on each MI that is explaining, and then these are these so yes. So yeah, I didn't finish. There was one more thing that we will actually need. So let me just get to this. So the idea is the following now. So yeah, I said it's the intermediate extension of QM, but this is a definition. So this construction that I explained here is actually the definition of what's called the intermediate extension of the constant sheaf from M. Sorry, M. So maybe sorry, from M. Smooth. So from the smooth part of M into the whole of M. Okay, that's this construction that I vaguely explained here is the definition of that. And you can define this as you will need this for a slightly more general situation when you have and this is what I refer to here. Suppose that you have a local system on any this is maybe MJ. Let's take another stratum, MJ, and let's look. You can take the trivial sheaf like I did it here, this QM here, but you can actually take any local system on it. So it doesn't have to be a trivial local system on the stratum. And then you can follow this procedure similarly, and you can define an intermediate extension of that sheaf into the lower stratum. Okay, so we'll need this, and I'll denote it by IXMJL. So I introduce a symbol which says that you take, which from this data, local system on a particular stratum, an intermediate extension of that local system to all the local strata, and I think of this as this is a sheaf on M. I'll think of this as a sheaf on the whole thing. Of course, it will be only supported on MJ because and the closure of MJ. Sorry, I went through this very quickly, but hopefully some other parts will be understand. But here, I just want to say that there is a completely concrete procedure using these models that now I lost my pointer again. We'll come back. That allows us to actually calculate intersection cohomology. Find a model. Okay. Now the major tool, the most fundamental thing, is what's called the decomposition theorem. Okay. So the decomposition theorem is the following thing that's written just here, and it's the following thing is that you take so we take our singular and maintain this M to be the singular variety M, and then I take a variety X which is smooth, and so this is a particular version. There's more general ones, but the ones we use, the version of the decomposition theorem is that I just look at, I suppose that there's a dominant map from X to M which I denote by pi. Okay. And the idea of the decomposition theorem that then I can take a sheaf upstairs, I can take the ones we are interested in is, I'll try and make this, I want this this I don't understand. Olga, and then she comes back somehow, right? I don't know when. Okay, so the idea is the following: is that I take the push forward of this, say, for example, this constant sheaf from the big space from X, and the result will be a direct sum of the kind of sheaves that I defined vaguely up here, intermediate extensions of some local system on some of the structure. That's the statement. So that any whatever you do, there is sort of this category for which this is actually not completely canonical, but usually, but any smooth sort of, so it's not a resolution because X could have higher dimensions, but any sort of the pseudo resolutions of the singularities will always result in the following thing. Now, of course, what is pi lower star qx? If you push it all the way down to the point, as I explained here, it's just the cohomology of the variety of X. So so what you see on the left-hand side essentially is just the cohomology of the variety, the smooth variety, is decomposed into these pieces having to do the strata of the map with some LIs, which are mysterious LIs. So this is an absolutely remarkable fact if you think about it. So this, and it also tells you, it gives you an idea how you can approach the intersection cohomology. If you find a nice map from a smooth variety, then you can hope that you'll have a bunch some direct summands, and you hope that the intersection cohomology that you're interested in are one of these pieces, and then you can maybe subtract. You can subtract from the left. So in our philosophy, what's happening here is that we understand the left-hand side here. We understand this pi lower star qx pushed all the way down to the point. That's just the cohomology of this smooth variety that you have control over. And on the right-hand side, you hope for some kind of subtraction. And this subtraction is this kind of has this analogy with the Atiyah-Bott subtraction that I was, and in some sense maybe they are similar, but it's not clear to me. But it's a similar kind of subtraction argument that we had there. So so let's see how that works. So I will explain now this subtraction algorithm. So up here I just okay, it came back. So here is this decomposition. It's just the same thing. And just a little remark that I mentioned is that when you, so of course if you take pi lower star qx and push it down all the way to a point, then you just get the cohomology of, so from here all the way here. Now of course you just get the cohomology of the right of x. That was the definition of cohomology, the push forward of the constant sheaf. But now we'll first just push it down to m. Well, if you do that, then it's easy. Well, it's essentially the definition is that you just get a sheaf whose fibers are the cohomologies whose stalks are the cohomology of the fibers. So again, you take a point P in M, you push it down, and it's just the stalks of this sheaf is just the cohomology of the fiber, the usual cohomology. So this is important. This is actually an incredibly confusing thing. So I'm sorry, now I'm talking about technical things. It's a very confusing thing. Is that when you do this push forward, then even though you work in intersection cohomology, the actual things that you get the stalks of the sheaf are usual cohomologies of singular varieties, which are the fibers. The fibers are often singular. It's kind of a very confusing thing. So there you don't take intersection cohomology, you take usual cohomologies. So that's what you.
And does it make sense to take intersection cohomology at some?
It makes some sense, but that theorem is not true. So it's different. This is a little strange, but that's why it's so amazing that it works. Actually, it's formula. But so again, remember that. So if I push it, I take this or this, whatever, take this pusher and push it all to the point, I will actually get the cohomology over the whole of X. So this way I get a decomposition. If I push these things separately to a point, I get a decomposition. I mean, which is kind of really amazing. Okay, so now I am explaining this. So I write optimistic is because I assume certain things. If you just do it for absolutely any case, it's not going to work. But in our case, it does work. So you need to verify some technical things. Suppose that they were true, then the following subtraction algorithm works now. So you So the idea is the following. You take a point, and so M0, just remember these indices here are the codimension of the strata. And what you do now is you look at this map XM, and you want to so you do the following: you kind of push forward this thing to M. So you look at this, and you want to represent it. So our purpose by a structural algorithm is to identify these summations, right? So that's what we like to do.
So now you are back in the setting of this correspondence?
No, not yet. But yeah, but I'm slowly getting there. You can think of it already that way, but this is a completely general thing. It works in general. I mean, so I haven't. Yeah. But you're right. I mean, it's sort of. But for now, I'm talking about the complete generality.
M0 is just some stratum.
So M, I know that by M that was script M. This is under M. But yeah, some M, some singular variety with some projective singular or projective variety, and you take this. The different strata. So MZ is the big stratum, the C, the smooth stratum. And so the point is, you want to exhaust this push forward, so to speak, right? So you push this forward, you kind of see what that over a generic point. So you take a generic point in M0, then over this generic point you have a generic fiber with pi inverse P, and you have its cohomology. Actually, in this case, it's going to be smooth necessarily. So that first thing is smooth. So that this fiber is the fiber of this pi lower star QX over a generic point P. Now, if you look here, obviously you need to get rid of that somehow. You need to recover that, right? So that means that you will have a piece which is IXT M0 and that generic fiber. So this thing is necessary. You basically need this. You'll have this. There will be definitely an IX M0 generic fiber, the cohomology of the generic fiber thing in this direct sum. That will be a sum. Because you need to get rid of it somehow. And if you go to smaller strata, they will not be able to. They are going to support. If you take sheaves that support in smaller strata, you will not be able to touch the M0 strata that way, right? So somehow you have to. So for that reason, you already know that this is necessary, and then of course you need to take this intermediate extension because that's what you have here. So you need that. So basically, the point is that the first step of the subtraction algorithm is that you a priori already know that L0, this thing, will be necessarily one of the summations. So if you know that, then you subtract it. That's the idea. So that's one thing that's usually not emphasized because I think in complete generality is not true, but in our case it is true, is that the way to subtract it is the following thing. I take this sheet now, this L0, and of course you remember, so over the generic fiber, this is just, it's just the stalk of the sheet is just the cohomology of the generic fiber. But when you do this intermediate extension, you go to the singular things, you get these cones that I was talking about. So you get these, they are much bigger. The stalks of the intermediate extension of this sheet are much bigger than the cohomology of the generic fiber. Okay, it's some bigger thing. It's a higher dimensional vector space that comes from the cohomology of those normal cones. Okay, so in any case, the claim is that, okay, you do that, so this thing could be kind of complicated. So you go now to point P on the next stratum, M1. So this L0 restricted to the point, the stalk, I mean, this L0 restricted to that point, M1, is a much bigger space than just the cohomology of the generic fiber, it's some other thing. But the claim is that here, there is a map from now the generic, the fiber over this point over in M1, which is different now. It's not the generic fiber because it's not generic. And there's a map from here to here, okay, which is surjective, right? And so the claim is a well-defined map. I can vaguely explain what it is, but it's not important. The point is you have this map, so and then you can take the kernel of this map, eta, And this kernel will be now a sheaf on M1, constructible sheaf on M1. So that's the end of the subtraction argument. You first, in principle, you obviously, some risk you can already see, you need to do two things. You need to find all of the cohomologies of these fibers of the map. So for all strata, there's a generic one, but there's the other ones. And then you need to understand these, calculate all these intermediate extensions inductively. And then you need to construct these maps from the cohomology of fibers to these intermediate extensions. Where are these maps? You get kernel, and that kernel is what I call subtraction, right? You subtract from the cohomology of the fiber the intermediate extension to the previous steps, and continue doing that. And then you go to the next thing. You go to the next level, the M2 stratum. You calculate well, you already subtracted, so you take the subtraction, you calculate, you subtract from this, you subtract this, and then that's the kernel, and then from this kernel, so this is the same. Kernel is this thing. And from this kernel, there's a map from L1, this is the intermediate extension of L1, at the point P, that comes from a previous, from the previous thing. You're going to subtract and then you continue. I mean, and every time the logic is that you are forced to subtract those things because in the lower dimensional strata, they cannot be supported anymore. So every time you go to stratum, something is left of this sheet, basically. That thing you have to take away, right? Because there's never later, when you go down in the strata, they cannot be subtracted anymore. And so this is actually a well-defined algorithm under some conditions to recover fully this direct sum decomposition. So when I talk to the experts on intersection cohomology on these maps, and they always tell you that you cannot calculate actually easily these summands, but actually we did. So I don't know. I guess there's some more general cases when it's more difficult to calculate. But actually, we use this algorithm, and we did calculate in this case. It's true certain conditions have to hold. So in particular, of course, usually there is perverse sheaves, there is complexes. They need to kind of split or be supported in some dimensions. So there's certain technical conditions, but they do work in this case. So these are subtraction algorithms that we perform. And so after that, it's sort of basically, as I said, there's just two. So now we have to apply it to our case. So we apply it to our map P going to M.
I'm sorry, excuse me. In the previous slide, maps QY is beta, P is rejected.
Why is it rejected?
Yeah.
He didn't find the map, so he cannot say why it's rejected.
No, but I can say why it's rejected, even if I don't define it. Because yeah, I mean, because it follows from subtraction. I mean, see, so yeah, it follows from what I said. So let's try this again. So just so that's some other point. So you agree that there is a theorem like this, and this is now I look at locally. So I look at the push for Q to M. I obtain the sheaf, which we don't know how to, which we know very easy to identify. This is the sheaf. These are the stones, the cohomologies. Okay. Now here, these are necessary. That's the big theorem. That it's a necessary intermediate extension local system. So now the first step was we started at M0, and there we know what the fibers are. So necessarily this thing has to be a direct summand. Okay, so if that's a direct summand, I take its intermediate extension. Now I have two sheaves on M1. The fiber sheaf, so this just this thing, and this intermediate extension is L0. You have these two things. And so the point is, I know that it's a direct summand, so this thing needs to be bigger than this. You see? Because I mean, there's something I'll add on M1, and the sum of that will be the fiber, the cohomology of the fiber. See? So there's something missing. Yeah. Now, why? So in that sense, intuitively, that's why you need some extra piece. That's why this is bigger than this. The fact why there's a map from here to here, and the first step actually I can explain it. It's very simple. I mean, it's just because you are at M1, and then locally it's a theorem that well, you in a transverse direction, then locally you just so you take looks like this. You're in M1. This is M1. Okay, you take a point. So the claim is that when you take a transverse slice, then and you take the inverse image of this transverse slice, then that the inverse image is contractible to the central fiber, the fiber over M1. And so what that means is that you have a map that not injection, we call it well, an injective map from the inverse image. So basically a map from pi inverse of the slice minus the point into the pi inverse of the point. This is under equal master. This is a set. So what am I saying? Just remember, this is simple. It's just what I mean is that I take I take this slice. Of course, the slice minus the point is a subset of the slice. But when I take pi inverse, then pi inverse of the slice has the same cohomology. Oh, sorry, it's cohomology. The cohomology of the slice is the same as the cohomology of the inverse image of the slice, the same as the cohomology of the point. And of course, this is smaller if you throw away the point. So there's a map then, there's an inject. It goes then, and then when you do the cohomology, it goes in the other way, the map. And that map is well defined. This is completely well defined. And because of this subtraction thing, this has to be surjective. So this map I can define at the first step, it's easy to define. It just comes from this step. Okay. Now later you need to, but in a sense later it's also true, but the map is a little more difficult to define because then you have intersection cohomology and but at the first step you just have usual cohomologies, and it's just it. Okay, so now we apply this to our map, this pi, you remember, that we got from the parabolic, so that space of what I denote by P1, right? And going to M0. And so now I have to deal with the strata. So I'll just, very general, I will follow the strategy that I described. And, but so let's just talk a little bit about the strata. That's the first approximation is very simple. I already discussed this, that if you take M0, then the elements look like this. So there are semi-stable bundles, but actually we'll look at what's called polystable bundles. And so the points of M0 are all what's called polystable bundles. So I fix a partition R of the rank R, the sum of R, R, is lambda. And then this M lambda is just the set of bundles in M0, which can be described as the direct sum of stable bundles, of degree 0, that's important. Degree of VI is 0. And of course, the rank VI is Ri. So we look at these are the strata, right? They are not exactly the strata. This is still not smooth, actually. You have to be a little careful because you have these, but now I'll correct that. So these are just subsets now, this M lambda. Now I will define then what we discussed yesterday, maybe you asked me yesterday. So I'll define the non-degenerate bundles, which are the following. So you write them the same way, but you assume that there are no two isomorphic components. So that implies, you think about it, is that this normal slice that I was talking about is toric. The group, the automorphous group is toric, is commutative. So if this condition holds, then the automorphous group of the bundle V is commutative. And I'll call this one non-degenerate or toric, this subset. And the proposition is that if I follow the subtraction algorithm that I explained, that these strata, the degenerate strata, so that are not like this, do not contribute. So you need to prove that separately. But it's very useful because if they do not contribute, then from now on you can also have to look at the toric strata. So I call them toric, right? Because what I wrote down here somewhere, here, and this is the case when this automorphous group, right? Since there are no two components are the same, the automorphous group is a toric, is a commutative group. It's just C star, and the quotient is just a toric variety. But this toric variety could be very singular, but still, its theory is known to some extent. Yeah, here. So this is the first. This is an important statement. So if you do these things by hand, then it's kind of, you see it. If you do it from outside, it's maybe it's less obvious. And so from here on, then you just have to perform the algorithm that I described. So roughly, I just give you a vague idea what you have to, the work you have to do. So I will not be able to explain what it is. So what is the work you have to do? So basically, what you need to do is for every point, but now actually we'll only care from now on about these non-degenerate points. For every point in monomoduli space, so that means every vector bundle which satisfies, for example, in M lambda, which satisfies this condition, you need to look at the fiber. I need to identify what it is. And roughly, those fibers will be sort of towers of projective spaces, and then they're glued together in some way. So they're singular, but you can control how they're glued together. So you look at a non-degenerate bundle, so, and then the fiber roughly looks like this. So you fix an order of these, so the sigma is a permutation. So you fix an order of these components, and then you will look at bundle V tilde, whose components are in this order, the bundles, the components of VI in a particular order. Right? So what this means is that so basically you'll be looking for vector bundles which are not necessarily direct sums of these bundles, but sums for Jordan-Holder decomposition as components which are these bundles. Okay, so and though if you list those bundles with some parabolic structure, then you precisely get these towers of projective spaces. And then you get a tower of projective spaces for each permutation. So you have k factorial such towers, and you need to glue them together, follow a little bit what's happening, and that's the identification of these fibers. And so so you do this, and so so here I wrote what is really happening. So if you want to identify the fibers, you get these some projective towers corresponding to each sigma, and you study them separately. So sigma in Sk, and then you need to glue them together along a certain subsets which you need to follow, and then that's the answer. Okay, so this is some geometric calculation you need to perform. And then the second part is to understand these local cones, as I said, these intermediate extensions. That's also some work. So I would like to just finish a little bit explaining this thing, because this is really a very beautiful, completely independent piece of work. And it's kind of interesting because this is probably one of the most natural toric varieties that you can write down, but actually nobody managed to calculate its invariance. At least we didn't find anything in the literature. So it's basically the following thing. Roughly what you need to do, well, let's even start here already. What you're doing is the following. You take a Lie algebra, say the Lie algebra SL3, and well, you ignore the Cartan, so you only look at the weight space. So basically you take all off diagonal, if you like, look at it this way. Okay. So if you like, you can just take 3 by 3 matrices which have 0 on the diagonal. Okay, so you have a 6-dimensional space that's left. And you act on that 6-dimensional space by conjugation by the diagonal torus, this T. Okay, so you look at that variety. So if you like it, take just the affine quotient, so affine invariance of that thing, that space. So the weights of those invariants, that's what appears here, are just the roots of the XL3, this alpha I minus alpha j for all ij. So you take that. You take that quotient, obviously you obtain a toric variety, right? Because it said when you take a vector space and you divide it by C star, actually you always obtain a toric variety. So this is actually obviously the toric variety that we'll have. Of course, it's very singular, but it's basically, if you like, it's for some sort of compactification or something of Lie algebra. So that seems like one of the most natural things you can look at, but it actually is rather complicated, and if you don't know the answer, it's kind of hard to see about. So what we need to do, this y lambda, is precisely one of these things, except this epsilon ij, what it says here. So you take a vector space, which will be our h1 and that I was talking about, and you divide it by these. So the C star, the torus acts like the cartan acts by the usual roots, but they have some multiplicities. So the roots, so it's the same weight appears several times. That's what this epsilon ij means. But anyway, you can just think of it as this problem. And you need to calculate. You do that, and of course you get some very singular variety, and you need to calculate its primitive cohomology. And that's not so easy. So then you have to do that work, of course. And so because we knew the answer, the form we wanted to know, so we kind of, then you can do it. But if you don't know the answer, then it just looks. And people looked at these things. I mean, but if you don't know what you're looking for, it's not so easy to find the primitive intersection. So you need the primitive intersection cohomology of these varieties. But this is a very natural question, though. In people look at these primitive cohomologies. As I mentioned last time, actually, people who have looked at primitive cohomology of just products of projective spaces, already that is a non-trivial combinatorial problem. Even though it looks simple, if you actually want the formula, it's not so easy. So this is an order of magnitude more difficult problem. And as I said, this was not solved. It is not known as far as I know. So we needed to solve this problem as well. So you do that, and then you perform this. So these are the two elements. So as I mentioned, cohomology of the fibers and this toric problem. Once you know that only the toric points contribute, you do this subtraction algorithm and you recover that original formula basically. Okay. So maybe I'll finish by maybe I'll just explain a little bit. So at the very beginning of what it looks like for rank 2, for example. So what already that is not completely trivial. So let's just look at the rank 2 example. And I'll stop. Maybe I have like maybe 5 minutes something. Start a little later. The rank 2 case. So the way we actually, where this started was the following. So in rank 2 case, you just had P1, which is you have this M1, and of course the cohomology of this space are very well known. And this also was known in various ways. M0, and this, in fact, what I'm telling you now I found later. Actually, I found the paper of Team. Actually, he already found this very expert. But this is a special case of that formula. And so what happens here? So again, this here is now a P1 bundle, right? P1 bundle on M1. So this P1 is just one higher dimensional than M1, and it's a P1 bundle because you just choose a line in the fiber of this M1 point, and then this one is generically a P1 bundle, but otherwise, roughly what you have here, I can actually even tell you what you get. So the fibers so then inside here you have the singular strata, and they look like this. There is a strata which is the M11 strata. So the 1 has nothing to do with the degree, it's this lambda. So the rank, the number 2 only has one partition basically. I mean 2, 0 and 1, 1. So the 2, 0 is the open stratum, and then the 1, 1 is a special one. And inside you have so this is actually, so this M11 is actually just equal to the Kummer, if you know what that is. It's the Kummer. All right? So it's just the Jacobian times the Jacobian divided by exchanging the two terms. And then well here, it's essentially the Kummer times the Jacobian. So that's of course when you have the direct sum of two things. And if you take a point, maybe I can also, because it's so simple here, I'll actually tell you what you get. If you take a point here, but a generic one, so a P, so this is not a non-degenerate in the sense that I was talking about before, then P inverse of this is just going to be equal to, it's going to look like just two projective spaces actually, like this, and they're joined at one point only, and this is PG minus 1, PG minus 1. So two projective spaces, PG minus 1 joined at a point, that's the singularity. So that's what this looks like. So you have basically that's like, for this gives you a good idea. You have M0. So in the C, in the open part, you have a P1 bundle, generically P1. In the Kummer part, you have P much bigger dimension, PG minus 1, PG minus 1, and they're glued at one point. And then of course you have the degenerate points, and they are actually, in this case, it's easy to see that it's a PG minus 1, but actually we don't need it because, as I said, they don't contribute. Okay, and now, but now if you look at our formula, then what happens is that roughly, yeah, maybe I'll just go back to the formula and try to find it. So let's look at this formula. So at the very beginning, for this rank 2 case, what happens is that you have sort of almost the same thing. When you do this exponential, of course, for the when the key Q is 1 here, then basically you just have this and this in the two. When you expand this equation, basically what I'm trying to say is that you can just subtract from this, you can just subtract this, and what you get is this contribution over the 1, 1 fiber, which comes from the R equals 1 term here. Okay, so it's very natural. What I'm trying to just say that it's very natural to subtract this from this, right? Because when you take the exponential, the degree 1 is just okay, and the difference is a small thing that comes from the 1, 1 piece. Okay, so let's do that. So all I'm trying to say now is that if you now subtract simply from the Poincare polynomial of M1, the intersection Poincare polynomial of M0, sorry, yeah. Well, okay, let's multiply it by P1, it's not so important. But by the same thing. If you do, then actually you get something, you get essentially something on the Kummer, the symmetric product. And so now don't have time to fix it precisely, but it will give you an idea. So what you get is kind of very amusing. So what you get is either you get the Kummer or the anti-Kummer, if you like, depending on the genus. So you get the even cohomology of the Jacobian, basically of the Jacobian. If the genus is, now I'm going to screw this up probably, but it's odd. No, I forget now. And the odd homology of the Jacobian if G. So depending on the genus, the subtraction argument actually, because of this, you have this low. So what happens is that on that you do the subtraction argument and you get a one-dimensional piece. So you do the subtraction argument to subtract from the cohomology of this glued thing, the cohomology of this normal cone, and you'll have a single one-dimensional piece that's left. But that local system that you get of that is non-trivial, and depending on the genus, it's either even or odd. And when you do the push forward, that has this effect. Actually, this is the first thing you notice when you do this, that you just do the subtract the two things and you get this strange difference in the genus. And then I try to explain this, and then slowly from that on, it's this thing got together. But so if you can actually do, you look at the formulas and you see this effect, then that's what it comes from.
Thank you.